Hello everyone, my name is Wayne Swink, and today I'll be presenting on AI phenotyping software for industrial hemp. This project is part of my coursework for ALEC 640, Methods of Technological Change. The work connects my research at the USDA ARS with my PhD studies at Texas A&M University. Today I'll walk you through the need, the innovation, and the potential impacts of applying 3D AI imaging to industrial hemp breeding programs. At the USDA ARS, within the Cotton Quality and Innovation Unit, which I work for, we operate as a problem-solving service for both the public and industry stakeholders. Our research spans a range of natural and synthetic fibers from cotton and hemp to coconut, banana, and even cellulosic-based materials. Our mission is to create novel products, innovate processes, and create value-added opportunities for natural fibers. As industrial hemp reemerges after decades of prohibition, research programs like ours play a major role in building foundational knowledge, metrics, and tools that help the industry grow responsibly and competitively. The learning objective for this presentation is straightforward. By the end, you should understand how machine learning and 3D image processing can be applied to capture the morphology of hemp stalks and how that enhances phenotyping and plant breeding programs. This is an emerging area where AI is not replacing human breeders, but augmenting their work with faster, more objective, and more comprehensive data sets. So let's talk about the innovation behind this 3D concept. According to Kahn's 2018 definition from the article Understanding Innovation, product innovation is any new product, service, or program offered to the market. In agriculture, AI-based image analysis is already being used in the field to do things such as detect insects, weeds, and diseases. But no current AI product exists specifically for 3D phenotyping of hemp stalks for fiber breeding. Our partnership with Breeding Insights, LLC, enables us to introduce a new imaging software package tailored to industrial hemp stalk morphology. For industry stakeholders, this is a new category entry, meaning it isn't new technology offered to consumers, but it's new to the companies and institutions developing it. In this case, it's a new category entry for Breeding Insights and the USDA. For plant breeding programs, this has the potential to fundamentally change early generation selection strategies, or in other words, it should help you pick good parents across for the desired traits you want out of your crops. So on this slide, I've included a short video from the KWS group. This group talks about their project involving robotics and AI and phenotyping in the greenhouse. It also highlights how AI shapes human decision making and how humans shape AI. This is important because AI systems are only as good as the model training, calibration, and data diversity behind them. In our case, human expertise determines which phenotypic traits matter, how stocks should be prepared and imaged, and how the model should interpret certain plant structures. All of this may correlate with fiber quality and biomass yield. So let's watch the video.
Digital solutions have long been in widespread use outside in fields. Now at the seed breeding company KWS, these solutions are increasingly moving into the protected area of the greenhouse. Biologists and physicists at KWS are using a sophisticated system for phenotyping corn and sugar beet plants in their research on the complex trait drought stress. State-of-the-art camera and sensor technology, robots, and artificial intelligence are supporting their work. In the greenhouse, the phenotype, meaning the external appearance of corn and sugar beet plants, is being measured and analyzed in detail. In this way, both the influence of environmental factors and the influence of the plant's genetic resources can be recorded. The PhenoFactory's color and spectral cameras take pictures of the plants. The images show how the plant's shape, size, and weight change as they develop. Visual traits such as these provide important clues about the drought tolerance of the plants. The researchers still don't know which genes plants actively switch on when they experience drought stress, but the technology enables them to collect data 24 hours a day, 365 days a year. The in-depth understanding gained by taking this approach is important for effectively supporting the breeding of drought-tolerant varieties in the future as well.
The reason my unit decided to do a phenotyping project involving AI is because our team currently manages the largest accession of hemp stock samples in the US. We have more than 100 genotypes, ranging from fiber type to feral accessions. Because hemp was criminalized over 80 years ago, the research gap is massive. We're currently trying to make up for decades of lost time. So growers, processors, and policy stakeholders are looking towards researchers for accurate, objective data to support the reestablishment of their industry. For researchers, AI imaging helps us standardize image across environments and seasons, record morphological traits that influence mechanical processing performance, apply phenotype to genotype mapping using modern genomic tools, and identify promising lines earlier with greater confidence. In hemp fiber breeding programs, the end use determines which traits breeders prioritize. For textile production, breeders want long, continuous bast fibers, fewer stem nodes, and reduced geometric irregularities. For people who are growing hemp for, say, animal bedding, breeders may prioritize high volume of woody core, which is called the herd, thicker stems, and faster maturing plants. On the processing side, or as the industry calls it, the decortication side, manufacturers care about how easily stems pass through their equipment, how much energy is required for decortication, and they're really focused on the durability and lifespan of their machinery. All of these rely on stem morphology data, and AI helps us to capture it at scale. So phenotyping hemp stalks is usually done manually, usually done by hand. And of course, that means higher labor demands, significant time investment, inconsistent measurements, and incomplete data sets due to limited data capture. Manual methods simply cannot provide the resolution plant breeders need, especially in our case, where we have 100 plus genotypes across multiple environments. There are many digital phenotyping tools that exist nowadays, but none of them meet the needs of hempstock morphology. For example, RDQ focuses on disease quantification for seedlings. OpenPheno is a smartphone-based app, but it's limited to 2D images. FieldBook improves data collection efficiency, but it doesn't support 3D analysis either. What's really important about the three that I put on this list here is that I've actually contacted these groups, and they've all confirmed that they currently cannot support hemp plant imaging and analysis. This is good for us. This technology gap is precisely where our innovation fits. By introducing a 3D AI-based system to hemp crops, we gain immediate advantages. First, objectivity to measurements is standardized regardless of who's collecting information. Using 3D instead of 2D, we capture depth, curvature, and geometry not visible in 2D. With the AI system, the model learns morphological differences among and within genotypes. Data reporting speed increases because computations are performed almost instantaneously. And on top of that, we are categorizing samples that are digitally preserved, even though once we start processing, the physical stocks end up being destroyed and that information is lost. This slide highlights what I had said before in the previous slide about stem morphology being lost after processing. In hemp processing, the stalks are destroyed to extract biomass. Decortication or mechanical processing removes the outer bast fiber or bark from the woody core of individual stalks. Once a stock is processed, its morphology is gone forever. Without digital 3D models, we can't go back and examine rendered representations of those samples. AI imaging preserves this data for us permanently, giving breeders and researchers a catalog that we can go back and reference long after the material is processed. So in these pictures, it kind of just quickly explains this post-harvesting steps to extract fiber. So we go from harvesting to debranching to decorticating hemp into straw, we call it, and then mechanically opening that straw to produce suitable raw hemp fiber for spinning yarn. Everything we've gone over so far brings us to the core concept of the project. CQI and Breeding Insights are using 3D scanning and AI-driven image analysis to create full reconstructions of hemp stems. The idea behind the AI system is to capture a mesh model that can be analyzed for user-selected parameters that allow breeders to correlate morphology with fiber quality, equipment compatibility, and genotype performance. This video shows how we, CQI, use a robotic arm to scan hemp stalks, and the picture shows to the right shows several completed scanned hemp stems. Once the CQI unit completes scanning, they then send those images over to Breeding Insights, who does all the heavy lifting. They are developing the software platform, imaging technology, and computational infrastructure to make the software feasible. Their system integrates multi-camera 3D scanning, automated mesh reconstruction, AI parameter extraction, and cloud-based storage. This collaboration is pretty unique. It allows us to combine USDA's vast germplasm with cutting-edge imaging capabilities. So on the next slide is a video produced by Breeding Insights that explains their mission.
Welcome to Breeding Insight. We are so glad you are interested in learning more about us. Breeding Insight is funded by the USDA ARS, is housed at Cornell University, and was launched in 2018 with the hope to level the playing field for specialty crop, plant, and animal breeders. Breeding Insight works with USDA ARS breeders in various places all across the United States. BI has grown significantly since our inception in 2018. With our most current Phase 3 onboarding, we will be working with 27 different species and 59 amazing breeding programs that include both plants and animals. We strive to assist each of these USDA breeding teams while also balancing the variety and number of programs and species that we work with. Here at BI, we know that running a USDA ARS breeding program takes a lot of time and expertise. We are here to offer breeders support and funding to reach breeding program goals in the most efficient and beneficial way possible. Often breeders are faced with having to do it all: planting, analysis, sampling, image capture, and all the other aspects of running their program. At BI, we understand the challenges that breeders face, and we offer the various expertise of our staff to help. We know that breeders need various supports in order to make good progress in their programs. That means handling trait data storage, sample management, field data collection, genomic analysis, and decision support and reporting. We work together with breeders to remove breeding program blockers. Not having enough staff and targeted expertise, or a lack of funding, block breeders from being able to use technology and other various tools to move closer to their goals. Breeding Insight provides multiple species and breeding programs with targeted support across a variety of these domains. We are able to do that because here at BI, our staff is well versed in all of these areas. We have experts in genomics, IT software support, bioinformatics, breeding best practices, phenomics, technology integration, data management, data curation, and training. Each USDA breeding program is matched with a point person, a BI coordinator, but all of our staff work together on various projects so that breeding programs still get access to all the other expertise that we can offer. We welcome you to learn more about Breeding Insight and our mission and support of USDA ARS breeding programs by visiting breedinginsight.org.
Breeding Insights is still developing their technology, the software platform, but so far I just wanted to give you some examples of the parameters that they've developed so far. Right now, the information that we can collect are total length along the stem's central backbone, surface area of the entire mesh, cross-sectional diameter and area at the midpoint between nodes, node count, including opposite and alternate arrangement, and the shape and curvature metrics along the stem. These are highly relevant metrics to plant breeders, geneticists, and fiber processors. Previous methods could only approximate these traits. AI allows us to quantify them. Now, if you look at this picture of the stem, it's an earlier 3D scan of one of our stems while we were still trying to figure out the system, but I've kind of just added some arrows and some ideas of the metrics that Breeding Insights is developing. We hope to achieve a few goals with this project. Firstly, the phenotypic data that we collect from this project is actually going into a GWAS project with the USDA's Plant Genetic Resources Unit. And if anybody wants to know what GWAS stands for, or doesn't know what GWAS stands for, it's a genome-wide association study. We also hope to develop a publicly accessible application to support hemp breeding programs. We also want to refine and train the machine learning model to improve accuracy and add new features over time. We hope to expand the product line as additional traits become more important to breeders and industry partners. Ultimately, we hope this project bridges technological innovation with plant breeding, genetics, and agricultural engineering. Overall, AI enables us to capture data that hemp breeders have never been able to collect before. It bridges the gap between phenotype and genotype and supports a modern data-driven industrial hemp industry. As new genotypes, environments, and imaging techniques emerge, this platform will continue to evolve. So with everything in mind, I want to thank you for viewing my presentation. And on the next slide is a mini quiz. You're welcome to complete it. And again, thank you for your time.